Question 2. Here we have a question asking us first to find the range for a projectile with a certain initial speed, or maximum range rather, and then we're told if it has to hit a certain point on the ground, what are the possible angle or angles it can be fired at. So firstly, you need to acknowledge that maximum range means 45 degrees. Now that's only true when something is being fired from the ground and it's hitting the ground, or at least it's landing at the same level that it's fired at. If that level is different, the angle differs from 45 degrees if you want to maximise the range. But this is all ground level, so let's sketch it. 45 degrees is our angle there, because we want to maximise the range. Now we want to hit this point over here. I'm going to give it coordinates D0. D is our range. That's what we're trying to find. Okay. Set up your suvat. S is the point we want to hit as a position vector. U, now think carefully about this. You've got the two components of the initial velocity. So the one touching the angle, the horizontal one, will be 210 cos, because it's adjacent to the angle. So 210 cos 45 and 210 sine 45 for the vertical component. V we don't care about. A, as normal, is minus gravity. T is always just T. So don't forget, there's normally 5 suvat equations, but in 2D or more than one dimension, you don't have one of those. You don't have the v squared equals u squared plus 2as1, because to get that into vector form you need to use something called the dot product, which is beyond the scope of A-level maths. Now, I need plenty of space. So there's our old friend s equals ut plus half at squared. Chuck everything in. Split into 2 separate equations. Now notice there that we've got 210 cos 45 times t, and the neatest way of writing that is to snick the little t in there. So just a habit really that I'm in. Otherwise it looks like you're doing cos 45t, which you're not really doing without brackets. Expand the second equation, or the vertical equation if you will. Okay, now this equation's got 2 unknowns in it, d and t. This equation's got 1 unknown in it. So factorise it. And we've got t is 0, which we already knew that was a solution for having 0 height. That's where it starts. But there's the secondary solution. If you solve this whole bracket here equal to 0, stick it in your calculator, you get that 30.3 seconds. Okay, it's not a final answer. We need to substitute that back in to get d. So bang that in there, and we get, I've put 30.3 ... to remind myself to use the exact value, which is still saved on the calculator's display. So use the answer button. And we get d is exactly 4,500 metres. Marvellous. Now, let's explore the second part of this question. So imagine you're standing on the ground there with a cannon that can only fire at 210 metres per second. You can't change that. You have to hit this point over here. But if you fire at 45 degrees, you'll miss it. You'll end up somewhere over here. So if you want to hit a point closer, you either have to aim it on a low trajectory or a high trajectory. So we're expecting 2 answers here, 2 possible angles here. So let's set things up. Same as before, 210, we've got theta this time, unknown. Trying to hit this point over here, 3,600, 0. Set up your suvat. I'm doing it out the way up here. Nothing untoward here, but of course we've got theta. I've done that thing where I pressed the wrong button, sorry. There's our gravity. T is T. old friend s equals ut plus half at squared. Now let's substitute everything into it. Set up your two separate equations. Right, at this point, again, back over here, we had an equation with two unknowns, an equation with one unknown. So we solved the y one first and substituted into the first one. You can do that same thing here, or the other way around. It's up to you. But a good thing to spot here is that you've got, you can actually simplify the second equation, because we're not interested in where t is 0. Can you see that we can factorise this? Let's do that. I'm actually going to do it in the same line. So I'm just taking a t out there as a factor. And then if we set that second bracket there, this bracket equal to 0, like we did on the left-hand side of this page, then we get t equals 210 sine theta over 4.9. And that we can now substitute in here to eliminate t. So 3,600 is 210 t cos theta. And if you simplify that right-hand side and move that value, so basically we're dividing both sides by 210 squared and then timesing by 4.9, and we end up with this nice equation: 2/5 equals sine theta cos theta. How do we solve that? Well, you need to invoke this identity from pure maths, which we can rearrange by dividing by 2 to this. So we have sine theta cos theta is equal to half sine 2 theta. Okay, so 2/5 is equal to half sine 2 theta. Double both sides. 4/5 is equal to sine 2 theta. And we're solving that equation for values of theta in the range 0 to 90, because we wouldn't want to fire this projectile, more than 90 degrees, because it would go the wrong way. It would go over here. Okay, to solve equations like this, a clever thing to do is a substitution. Alpha, say, equals 2 theta. So our equation is now 4/5 equals sine alpha. And our range is, if we double all three parts of this range, the 0, the theta, and the 90, we get 0, 2 theta, and 180. But 2 theta is just alpha. So now we're solving this simpler equation. Shift sign 4/5, and we get 53.1 as a principal value. For sine, there's a quick sketch of the graph. We can see that we subtract from 180 to get a secondary value. So 180 minus 53.1 gives us a secondary value for alpha. And then to get theta, we just need to halve both of those. So 53.1 halved, remember to use the exact value on your calculator, 26.6. And if we halve 126.9, we get 63.4 degrees. And we're done.